Morning. Have any questions? We have a substitution question.
Yes.
Four, so I'm thank you. Right. That's fine. Let me try this one and 9 minus 4x squared. Basically, we have a 9 minus a square. This is actually 9 minus 2x squared. And we're trying to represent it in a way, so eventually this becomes something squared. Because this is under the roots, right? So if it's not equal to a square, we won't be able to get it out of the roots. So how we do it when we present you have cosine square of angle plus sine square of angle equal to 1. So then this is a summation. You can subtract. I guess just writing it really messy. I can write it on the computer and make it out there and easier to see. So knowing how to substitute the right way, it's really important for trig substitution. Because you may have the right direction, but not having the right direction is still work. So based on our formula, it said if you have a sine on your
Okay.
cosine and sine square of the angle. What cosine square, I guess I'll use it here last, will equal to 1. But we need a subtraction, so we're gonna subtract. I'm gonna subtract the sine square. So we subtract sine square from both sides of the equation. So sine square is equal to 1 minus sine square theta. This is fundamentally what we're using when we're doing a sign substitution. It's really all the A, B, C, they're all sign substitution. So, what we have in here is 9 minus 9 subtract. So you have to have a 9. The 4 is actually in there. So we multiply both sides by 9. Have 9 cosine square theta equal 9 minus 9 sine square theta. And now we have something identical to our question. The question has 9 minus 4x squared. So we're going to compare. We have 9 minus x squared compared to 9 minus 9 sine squared. These two are what's not matching, and we're trying to match them because we're hoping this will equal to this. It will equal to this. So basically, all three are going to be identical after the substitution. So to make the substitution right, you have to get this thing works. Oh, there was a 4, right? 9 minus 4x squared. There's a 4 there. So we have to have 4x squared equal to 9 sine squared theta. So that's that. From there, you solve for the x. So you created this 9 minus something squared. And that is what we're comparing to the original question. We have a 9 minus 4x squared, and that got equal to the 9 minus 9 sine squared, because 9 minus 9 sine squared equal to 9 cosine squared, and that making the root part become a perfect square. We will not be able to use the original one because you have no way to get a 1 to a 9 if we don't multiply everything by 9. So we kind of force have to multiply 9 to most that equation. All right, from there you can see that 4x squared equal to 9 sine squared. The rest is all algebra. We will divide both sides of the equation by 4. Then you have x squared equal to 9 over 4 sine squared. We have to get x by itself. So you have root of both sides of the equation. Root of the left side will be the x. X squared without the square is x, and then root of the 9 is 3. Root of 4 is 2. You still maintain that fraction numerator denominator. Root of the sine square is sine. Root of sine square is sine theta. So that is the correct substitution. I see that we often have a lot of difficulty whenever there's a high coefficient in there, but this is something very common. The substitution will kind of make everything work out. You can see what we have here is a 9 sine 9 over 4 that equal to the x squared. So that this is really the root of 9 cosine squared. So the root part is going to be equal to this. And then if you take the root of it, which is what happened in there, if you take root of it, it will become 3 cosine theta. So in this case, the whole integration becomes integration 1 over 3 cosine theta. And then the dx, you see that was an x. So dx equal to 3 over 2 cosine theta. That was a dx because that was an x. Therefore, this is a dx and the d theta. So the 3 will be canceled. The cosine theta will be canceled. You're gonna get integration of 1/2 d theta. And if you integrate this thing, the antiderivative is 1 over theta plus c. That finished whole integration. And then what is the theta? Theta, you have to get it from the inverse trick. So from here, you get sine theta equal to 2x over 3. So the theta equal to sine inverse 2x over 3. And the rest of the calculation will have a lot of difficulty as long as our substitution works out. So kind of try to finish the whole calculation there. But the original question is to make sure that we're able to do the right substitution. You see, let me scan this. That was interesting. Okay, that worked. Thank you. I think I got your answer in. I think I will have a little hard time if it works. Okay. All right, the answer should be B. Oh, C. Any question for the process? Are we okay? Do you have homework questions? Are we doing okay with the homework? 6.3. 6.3 homework. Are you guys finished? With anybody finished 6.3? No, but and if you haven't started 6.3, raise your hand. You haven't really started. You didn't start 6.3. What happened? Okay. But try to practice, okay? I mean, no matter how we talk about it, it's when you actually try it, you see real difficulty. The class is recorded. I try to identify what was trying to figure out where we are exactly. If we haven't started the homework, you will know where was the problem. So what about 6.2? Any question from 6.2? Homework question.
Question 10.
Question 10 on which section?
6.2.
6.2. Okay.
It's one of them.
Can we do this one?
This is the wrong one. I'm looking for the one with limits.
The one with
Yeah.
limit on this section? Okay.
12.
There's no limit on my version.
There we go.
Which one? This one?
Yeah.
Limit?
Over 2.
Over 2. That's question 9. Have you started?
I'm on that.
Question 9? Okay. Looks like it's a definite integral. The angle is not identical. We have 9 theta plus pi over 4. That is the angle for the first side, and then 9 theta for the second side. Whenever the angle is not the same, we have to use the product to sum. So let's try this. Question 9 on 6.2. What's going to be the question part? So basically what we are looking at is the multiplication of sine. So we use the formula, which is sine x times sine y. What is it equal to? You can find that formula online. Georgia, we can post it up. Yes, it is. We're talking about the formula. Yeah, product to sum is January 22. That day we have all these formulas. So essentially the first two is about the same. The negative sign comes from the reversion between x and y. Basically, if this x becomes the y, the y becomes the x, everything switch. So this one becomes y minus x. So if you switch it to x minus y, there's a negative sign. It comes from this difference. Here is all in the switch. So basically the first two equations are the same. The third one and the fourth one are new equation. We will find the last equation when we have a multiplication of two sine. Now, if it's a multiplication of two sine, the answer is 1 half. And here we're gonna have cosine of 3. We start with the subtraction, right? It's the x minus y. Let's see. Minus x plus 1. Basically the double angle formula, the addition angle formula and subtraction angle formula for cosine, have cosine and sine multiplies. So cosine x minus y is cosine x cosine y plus sine x sine y. Now cosine x plus y is cosine x cosine y minus sine x sine y. When you subtract these two, the cosine, the multiplication of cosine is subtracted, so the sine x sine y is remaining. You get 2 of sine x and 1, that's what we have to do. One half. Anyway, that was the formula. So we're gonna apply this, and let's see how we do it with our question. That was just the formula part, and then applying that formula is equal to focus on the indefinite integral. After we have the antiderivative, after we finish the indefinite integral, then we're gonna put in the number and calculate the derivative. So first we'll look at the formula, and then once we have the formula, we will look at the number. So we don't have to deal with the number, because even if we try to do with those numbers, are not going to be applied until the end. So now integration. So this is going to be the x, this is going to be the y. Then you match that. That's the x. That's the y. So find the formula. We'll have that. And here we're going to have the big subtraction. The first one is cosine of the two angles subtracted. We have 9 theta plus pi over 2 minus 9 theta, because these are the x and y. So x minus y. First one, you gotta have subtraction. So you know having cosine over here. That's the first one. All right, minus in the second one, we will be doing summation. So this is our first angle, this is our second angle, 9 theta, the second angle, 9 theta plus pi over 2 is the first angle. We add it together. When you are adding the angle, it's 9 theta plus 9 theta, which is 18 theta. So then that would you have cosine 18 theta. Again, pi over 4. So sorry. Sometimes I just look at it and outright writing completely different thing. So adding these two, 9 theta plus 9 theta is 18 theta. We still have to plus pi over 4. Okay. So that still be theta there. So this is applying the formula. According to the formula, these two are identical things, right? We didn't do anything. We're just writing it into a different format, because the original format is difficult to integrate. We're writing into a subtraction format now. Now we can integrate them one by one. And so we're going to integrate each one of them. The first term, it is really a number. Everybody can check out your calculator. Cosine pi over 4 is a special angle. It is actually equal to 2 over 2. So then the first integration is integrated with 1/2. And right here we have 2 over 2 times theta. So if you have a number, say 5, integration of 5 is 5 theta, or integration of 5 is 5x, depending on what's the variable. This one variable theta. So integrated, this is root 2 over 2, integration of root 2 over 2 is root 2 over 2 times theta, and minus. So we now need to integrate the cosine. When you're integrating cosine, the antiderivative for cosine is, what's the antiderivative for cosine? Sine. So we will have sine of the same angle. When you're integrating, we don't change the inside of the function. So sine have 18 theta plus pi over 4. And because of change, this is okay. This is the same. It's identical angle. But then on the outside, we're going to divide the 18. That was the chain rule. Or you can call that a substitution. If you make u equal to this, so that will be cosine u. But then du would have 18 theta. And if you want to have the theta, you have to have the 1 over u. That's why that division. Okay. But we normally don't revert back to the substitution method, because it's a simple substitution. Sometimes we just go ahead, write a division. All right. This is all done, I think. Let's see. All right, so now we have the antiderivative. That's finished with the indefinite integration. This is the indefinite integral. And I go back to the original question. We would evaluate it exactly at those values. If you find the value of this function when theta is pi over 2, theta. I mean, this function, if they put a 0, will have, well, let's calculate them both. So it would be easier when it's 0. Let's see what happens when we plug in number for pi over 2. It will be 1/2 and root 2 over 2 times pi over 2, and then minus sine of 18 theta, 18 times pi over 2. That's really 9 pi plus pi over 4. And this is over 18. That's the upper limit value. Lower limit is 1/2 root 2 over 2 times 0 minus sine 0 plus pi over 4. So sine pi over 4 over 18. So that's the lower limit value. And the rest you will use your calculator. Any questions? We use our calculator, or you can start calculating algebra. This one is root 2 over 2 as well. So that's negative is positive. So root 2 over 2, and then divided by 2, then divided by 18. That one is 2 over 2 times pi over 4. Let's see, we can put it in a calculator and see how the value is. The definite integral, so we actually need to figure out the number. Each kind of enlarge, so you can see what I'm writing. So we have 1 over 2 multiplied by, it's a subtraction. The first number is square 2 times pi, and then divide 2 by, so it's divided by 4. Right, the second number is sine of, is 9 pi plus pi over 4, so it's 9.25 times pi. So that was the sine divided by 18. That was upper limit value. Lower limit value is 1/2 multiplied by what's inside. It's negative sine pi over 4 is really square root of 2 divided by 2. And that has to be divided by 18. So really is divided by 36. Okay, so that was the evaluation of the final number. We will put it in. I mean, sometimes I'm treating the web work at my calculator. So that's what I entered. This is the antiderivative value at the upper limit of the integrated limit. This is the value of the antiderivative function at the lower limit at 0. When n equal to 0, this is 2 over 2 times 0. So therefore, I can write that part only right. That was the sine. 13. I wonder if you still have questions. Was it the same as your version of it? Yes. Okay. Any other questions? So this one applied the product to sum. Any other questions from Zoom?
6.3.
Which one? Number 1. Question 1 awesome. So that was root of a number minus a square. Options.
Can you show me the different setups for that, like the a minus x, x squared, whatever? I wasn't here.
Which one?
I know there's like 3 different combinations we can use. It's like number minus x, a.
Right.
Minus
Yes.
Yeah,
Yeah.
I don't know.
So basically, if it is a number minus x squared under the roots, we will be doing a sign substitution, make x equal to root of a times sine theta. If you have a root of a number, any number plus x squared will make x equal to root of a times tangent theta. A times tangent theta. If it's the root of the x squared minus other number, then we will have x equal to root of a secant, writing the two root of a times secant of theta. So those are the three type of substitution: sine substitution, tangent substitution, and secant substitution. When we have summation of square, we do tangent substitution. When we have number minus square, we do sine substitution. We have square of a variable minus a number, we do secant substitution. But this is a typical, this is the example when the x is by itself. I mean, if you get a minus 4x squared, then there's division by 2. I mean, if there's any other number before the square, it seems a little bit more complex. So we have to kind of look at them case by case. This is just indicating what kind of trick we're supposed to do. For example, in the question 1, we have 16 minus x squared. So that kind of fits the first scenario, right? So we will do x equal to 4. Are we okay? We okay? So if we follow that with the first example, we'll be doing x is equal to 4 times sine theta. Right, and then therefore dx, which is the differential, equal to 4 cosine theta. And I'm gonna start doing substitution. So this is equal to 1 over root of, if x equal to 4 sine theta, then x squared equal to 16 sine squared theta. So this is gonna be 16 minus 16. See, I'm trying to match. If you have 16 and you're gonna have a 16 for your trig or your trig function, so 16 sine squared theta. So the 16 will be a common factor. You can factor it outside of it. Anyway, the dx, right? Dx is differential. We now already have a formula for the dx. So that's 4 cosine theta. We okay so far? And then you can see the 16 minus 16 sine squared theta. You can bring the 16 outside. It's a common factor. So it's 16 times. To really work out the detailed substitution, this is 1 over root of 16 is common factor. And then there 1 minus sine squared theta. If you factor out the 16. Yeah, 1 minus sine squared theta is cosine squared. It's 4 cosine theta. Now we copy, right? Yeah, space. So this is equal to integration is still there. We're not doing things. We're simplifying. Root of 16 is 4. So this is 4, and there's a root of cosine squared theta. Because 1 minus sine squared equal to cosine squared. So over here we have 4 cosine theta. Right, so you can see the 4 is canceled. The root of cosine squared is cosine theta. So basically, this is a cosine theta at degree 1. That's a cosine theta at degree 1. There's a 4. There's 4. So they're all canceled. It's really it's integration of 1 d theta. So the antiderivative, which is d theta plus c. So that finished the integration. So from this integration of 1, that's still integration, but then now you have the antiderivative, now is theta. Theta is a substitution variable. We have to write it back to the original variable. Look for the integration, look for the substitution to find out the theta. So sine theta, solving for theta, so we got x theta by itself. Divide both sides by 4, so sine theta is x over 4. And then we're going to get rid of the sine using a sine inverse of both sides of the equation. Theta equal to sine inverse of x over 4. And right there, that's our theta. So the original question is sine inverse of x over 4. Plus c is on the outside, so then the final answer to the question will just be like a string. So that's the question number one. You might have a different number, you may have root of, 1/√9 minus x squared, 1/25 minus x squared, all that changes is the denominator. So for example, if you have root of, integration of 1/√25 minus x squared dx, the answer will be sine inverse of x over 5. So some people even collected all of these into a formula, but then I added a lot of different formulas to remember. I don't recommend having too many formula. Instead, try to follow the fundamental calculation. Question. Okay, so this is question one. Any other questions? Try for two. This is a number two. The question says use a substitution equal x equal to 5 and theta. So substitution is already given. And I guess the difficulty in this question will be in how to derive it. So this is number 2 on 6.3. Let me know if you have questions. Slow down. Right, this one, the substitution is already right there. So we don't have to worry about how to substitute. But this is indicated by this. We have x squared plus 25 squared. So we have to have a 25 also in the x squared. That's why this gotta be 25 tangent squared plus 25. That's why x has to be a 5 tangent. Because that way, if you square the x, you will get a 25 to match that 25. So anyway, this one, because we already have substitution, so then the dx will be the derivative tangent is secant squared. So dx is 5 times secant squared theta e theta. And then the substitution is how we replace every x. So this is equal to integration of 20 is immature. And then dx is all that. So the dx is multiply 5 secant squared theta e theta divided by x squared. X is 5 tangent theta. So x squared is 25 tangent squared theta. Right, and then we have root of x squared. X squared is 25 tangent squared theta plus 25. Then, and then we can see the numerator, simplify it a long way. The numerator will be, this is a 5, and there's a 20, so 20 times 5 is 100. We have 100 secant squared theta. Now in the denominator, we have to deal with the root part. The 25 tangent square stay there, and then this part, if you simplify, maybe we should simplify that part first. This part that was inside the roots, you can factor the 25. I mean, there's a plus, so that's 2 terms. Summation separate terms, so there's 2 terms in the roots. Between those 2 terms, they both have 25. You get the 25 out of those factors, and then you have tangent square theta plus 1. Tangent square theta plus 1 is secant square, so under the root, we have 25 secant square theta. And this is under the root, so when you put the root back on, all the root part will be 5 secant theta. So what we have is 5 secant theta. That's after we're removing the root. The ultimate reason for the substitution is we wish to have the roots go away. We want to get rid of the roots and replace it with something that's a little bit easier to handle. So after we've done that, you can see numerator and denominator have common factor, which is secant. There's a secant square and there's a secant. Oh, there's a secant. So these two, you cancel one of the secant, and then you have only 1 secant left. Another thing is the 100 divided by the 25 equals 4. So we have 4 secant theta e theta, and the denominator becomes tangent squared. Kind of slowly simplify this. Any question? You okay? Yes. Any steps that was not clear? So now we have this task of trying to simplify this. What I see is this, the tangent square is in the denominator, so whenever I'm not clear about the formatting of the question, I'll turn that to sine or cosine. So secant is 1 over cosine, tangent is tangent over cosine. So we write it all back into tangent over. Trying to figure out what do we go from here? How do we simplify from here? So I don't have a immediate formula to integrate it. That's why I'm trying to revert it back to sine and cosine. So secant is 1 over cosine. A lot of trigonometry there. And then the tangent is sine over cosine. So denominator is really sine squared theta over cosine squared theta e theta. So this is equal to integration of the cosine in the denominator. You divide fraction most by yes. Do we still have it was that's right. There is still a 5. Thank you. That's a good catch. There was a 5. I forget to write it down. There's still a 5 there. The secant was canceled from the numerator, but the 5 is still there. Still a 5. Thank you. Any other questions? All right, so we can multiply numerator and denominator by cosine squared just to get rid of the cosine square in the denominator. Try to get the cosine combined. So we multiply cosine square in the numerator and the denominator, which will cancel, mean that numerator that's not going to cancel. Then the numerator have a cosine square over cosine, that give us a cosine. Any question about this step? Okay, so the denominator's cosine will go away. Trying to simplify the whole thing. So numerator become 4 times cosine. And then denominator is sine square. Well, there's still 5 sine squares. Square theta d theta. All right, so this is now a little bit more clear that the derivative sign is cosine. So this is sine, derivative sign is cosine. So whenever the derivative of the function is multiplying the differential, you have a chance for a substitution method. Guess what should be the u? Substitution. U should be equal to anyone. We're solving this with substitution. What should be the u? We've done already a substitution. We're solving this. U equal to sine theta, right? Okay. So what we can do is we are making a substitution. We make u equal to sine theta. Then du would be cosine theta. Du will be cosine theta d theta. In that case, the numerator is for integration for du. I mean, you see the d theta times cosine theta. Cosine theta times theta is now du. So kind of concise them a little bit. The denominator is 5u squared. 5u squared. We want to integrate this, and let me grab a little bit more space. We want to integrate this. Notice this is a power function in the denominator. Sometimes people would worry about how to do it when there's fraction, but if the power in the denominator, you can write it into a negative power. So this is actually 4 over 5 u to the negative 2 power. We can integrate this with the power rule. This is equal to integration 4 over 5 u to the power of negative 2 du. So using the power rule, the antiderivative is 4 over 5 u to the power negative 1 over negative 1 plus c. That looks awful, but follow the power rule for integration. If the power is n, the antiderivative is n plus 1 over u to the n plus 1 power over 1. The negative 1 is the power. The negative 2 is the power, so negative 2 plus 1 is negative 1. That's the n plus 1. We okay for the integration. So now we finished. The integration is done. working on reverting the variable. This is actually 4/5, and then there's a negative. This negative sign, we put it to the negative there. So it's negative 1/u. I mean, when the u is negative power is the addition. Okay, u is equal to the sine theta. We put one sine theta, so what we actually have is negative 4/5, 1/sine theta plus c. And we know what sine theta from work on the triangle. This is our antiderivative after we've done the big part. We have to look at our substitution to find out exactly what was the sine theta. So that is reverting back to the variable. This is the substitution equation. So that tangent theta would equal to x/5. Tangent is x/5. We'll draw the triangle. Tangent is opposite over adjacent. The opposite is x, the adjacent is 5. That was the theta. Tangent theta is opposite over adjacent. So this hypotenuse will be whatever we have in the equation. That is our hypotenuse, the x squared plus 25. So now we finish analyzing the triangle. We would need the sine theta, or 1 the sine theta. So in this case, sine theta is equal to opposite over hypotenuse. So it's x over x squared plus 25. That's the sine theta. So what about the 1 theta? 1 theta is a reciprocal. So then that should be, so the 1 theta should be the root of x squared plus 25 over x. Space there. So let's try to rewrite this here. After the variable goes back here, it's kind of messy. It's negative 4/5 root of x squared plus 25 over x plus c. So, any question we are going to follow? So using the substitution to write the triangle. When we have the triangle, we can write any trig value for that triangle, and that's try to assist how we rewrite it back. So there, we can check if the calculation is right. And this one, the derivative is supposed to equal this. If you try to find the derivative of the function, you can tell if the derivative is right. We will probably have to do the function rule for the calculation. You will try to find the derivative of this function. We put the denominator squared, which is explained by x squared there, and then numerator to combine terms. Numerator a little bit longer, but let's see if this is okay. So it's negative 4/5. The numerator is square root of x squared plus 25. The denominator is x. That's final answer. That's what we're having over here. Just like out this is the final answer in the original variable. That's the integration theta variable. The negative 4/5, 1/u is the in the unit. We did it twice of substitution instead of this. We did u x equal to 5 tangent theta is a trig substitution. Also did over here u equal to sine theta. That's it's substitution. It's problem number 2. Any other questions? So I'm gonna start at 6.4. We also need to go through your assignment. If you see any difficulty, we can try it together. Right now, because if you haven't started, I'm not sure what was going on, so.
I finished 6.2 yesterday as well.
Okay. So 6.2 is okay? Okay, so this is the first two question on 6.3. Right, I'm gonna start a little on 6.4. But try to start your homework. I think we are, roughly the same pace as last time, with teaching this course, but I think we have to slowly moving forward. On average, we have 1 day or 2 day reflection. So I spend too much time on one section.
Yes.
All right, so send me any question as you go through the homework. You can email me, hey, I don't know, I don't know how to do this question. So we don't fall too much behind, and you have to at least go through a couple questions each day. So we don't want to wait, like you have 20 questions, you have to finish them in 2 days. We're hoping that once the homework is assigned, you do one, like 3 questions today and then 3 questions another day. So then we distribute them across a longer time frame rather than compile them, but put it off until it's overwhelming. Right? 6.4. Let me start a little because most of today's time is spent on reviewing. But I'm hoping that we can. I'm hoping that I'm not the only one doing the math. You guys go over some homework, then I'm probably gonna help you out. Feel free to send me a message about individual questions, problems, how did you start it, where did you get stuck, so that I can try to look at your personal situation. All right, 6.4, the title is called Partial Fraction Decomposition. And it's really about how we integrate big fractions, and what we call decomposition is trying to turn a big fraction into smaller fraction. So the smaller fraction can be easier to integrate. So this is about a basic collection of kind of question. In the textbook, there are some questions that are really difficult to decompose, but in the homework, I really didn't put too much difficult question. They're just some of the typical question. All right, so what we want to do in this section is being able to solve a question like this. So when we have a division, and this kind of question is also the kind that we don't have a formula for its solution. So what do? We see a fraction, and what happens if the denominator is degree 2. If the denominator is degree 1, which will be easier to integrate, for example, integration of 1 over x dx will be natural log of x. So integration of 1 over x minus 1, that's when the degree 1, will be natural log of x minus 1. So if the denominator is degree 1, we normally will integrate it using natural log. But if it's degree 2, how do we do it? What we can do is actually rewrite the fraction. And that's what we're calling partial fraction decomposition. We're decomposing the fraction into smaller fractions. Each one, of course, is a partial fraction. So then, for example, 1 over x squared minus 1 can be rewritten into the subtraction of 2 fractions. If you're integrating each one of these, integration on the left side, you integrate this to subtract it. So the big integration becomes subtraction of 2 smaller integration. Each one of these individually is degree 1. So if you're integrating this, it's a natural log. So we integrate. The original question becomes subtraction of 2 integration. Each one of these, you bring the coefficient 1 over 2 to the outside. It is 1/2 integration 1 over x minus 1 dx. Integration of 1 over x minus 1 is natural log x minus 1. So that makes, but the two are very similar. This second integration, you bring the 1/2 to the outside. You have 1 over x plus 1. That is a derivative natural log of x plus 1. Therefore, you have the derivative, this is the antiderivative. So the integration of these two are similar, and that can become a common pattern, a common way to integrate any function that has degree 1 in the numerator and a number in the denominator. A degree 1 in the denominator, a number in the numerator. Any question? As you can see, the effort in solving this question in the decomposition. So this equation I goes 1/x minus 1 equal to 1/2 over x minus 1 minus 1/2 over x plus 1. That is the main thing. So if you already have that, then following that integration will be a process of using the logarithm differentiation formula. All right, so then majority of the section will be working on unit fraction. How are we gonna be able to write those? And how do we know it's 1/2, 1/2? How do we know those fractions? So we're gonna try to look at the process of rewriting a fraction. That is what's called partial fraction decomposition. So the method is not integration method. It is really a way to rewrite your integration into easier integration. Then follow that, you have to use a typical integration formula. Right, so how do we exactly decompose a fraction? There are two types. The first one, we're calling it decomposing them into linear terms. So really it's about the denominator. Number one, you have to have a fraction. Suppose you have a fraction that you want to integrate, you have to look at the degree. This fraction, the numerator's degree has to be lower than the denominator here. P of x over q of x is the fraction. The numerator has to have a degree that is less than the denominator degree. The degree of p has to be lower than the degree of q. So numerator could be degree 2, denominator could be degree 3, or denominator could be degree 4, numerator could be degree 1. But if the numerator has a higher degree, what do we do? Whenever the numerator have a higher degree, we call that improper fraction. We have to finish the division and factor out, or finish division, find out the quotient, and turn that into a proper fraction. So this partial fraction decomposition, we only do it when the numerator have a lower degree. If the numerator have a higher degree, we rewrite it. So the numerator still have a lower degree. Anyway, so guarantee that then we don't worry about the numerator anymore, worry about the denominator. So any fraction, the main problem is in the denominator. So we kind of have to see what kind of denominator happened that dictate what kind of fraction we're going to decompose it into. So number one, suppose the denominator has linear term. So it has factors such as x minus a. So if x minus a divide the denominator, if the denominator has x minus a to a certain power, then we have to determine what kind of power does it have. Does it have x minus a with power 1, or does it have x minus a to the power n? So whatever that power is, however that power is, it determines how many terms we're getting it, or how many parts it's decomposing to. So if it has a higher power, such as 5, and then it decomposes into a number over x minus a, a number over x minus a squared, until a number over, those are just representing the number over x minus a to the power 5. Now, if the x minus a is degree 2, then you only get a number over x minus a plus a number over x minus a squared. There's only, so the power of the x minus a is determining how many fractions we're getting. We're writing it out to this possible power, and this is really abstract. So then we're just talking about the scenario. All right, and then we're gonna look at an example. This is not the example, this is just a theory. And so let's talk about another one. The other one is, what if we have irreducible pedestrian? When do we have irreducible factor? That is when we have a denominator that's not degree 1. It's a factor of the q of x, which all talking about the denominator. If q of x has those things, that's not x minus, it's not x minus a number, not a degree 1 term. It's a degree 2. Degree 2 polynomial that was a factor. This goes back to the theory that all polynomial can be factored into x minus a number if the number is a complex number. So for example, if you have degree 5 polynomial, it can be decomposed into x minus a number times x minus another number times x minus another number, 5 of them multiplied together. But those number might be complex number, and we don't want complex number to be the coefficient. So when the complex number is the root, like imaginary number being the root, so we tend to combine them. In pre-calculus, we also learned that if we have complex number as the root of polynomial, we often count in conjugate. So those two multiplied together will end up giving you this irreducible geometric terms. So anyway, those are the only two possible factors of the Q of X of the denominator. That's why we only talk about these two scenarios. So the second scenario is if you have degree 2 factors in the Q of X, and then we still have to look at the power of that one. And let's suppose the power is n, and you're gonna get n of those decomposed terms. Now, in this case, if the denominator is numerator have to have a lower degree, they all have to be proper fractions. So this degree 2, the numerator is degree 1. So b of x plus c, that's a degree 1 function compared to the denominator degree 2 function. All numerator is degree 1. So we don't have any, even if the denominator is square of a degree 2 term, the numerator is still degree 1. That's the ability of decomposing them, so that we have way smaller numerator after they're decomposed. So it's easier to integrate them after we have those small fractions. All right, so those are just the ideas, and let's look at a couple of common. Number one, if decomposing a fractional function is similar to decomposed fractions. Here, putting a couple examples here. So for example, 1/6, the factor in 6 is 2 and 3. So you can factor this into two small fraction, 1/2 minus 1/3, 6 times 2 and 3. Another one is 1/18. 1/18 has 2, 3, 3. So 18 is equal to 2 times 3 squared, degree 2. So if you factor in that, if you write that into smaller fractions, it's 1/2 minus 1/3 minus 1/9. So you see two of these because that one has the power 2. So you not only do we have 1/3, we also have 1/9 because of the power 2. So the highest power dictate how many terms you have. There's only one 2 in the 18. So there's only one term. Anyway, so it's a similar scenario. But how do we do it? Let's try to follow the idea that we already talked about with more of a function example. So this example that you have in the textbook. So basically, when you're rewriting it, when you're decomposing it, the number one thing is we are writing a form with number that we don't know. We know there's a number there, but we don't know what they are. So for example, this one, it's not finished. It's just forming the decomposition. So if we get this big fraction that we wish to decompose, then you can see there's many factors in the denominator. It has x plus 5. So then the x plus 5 is a linear term with degree 1. So when you try to decompose this big fraction, one of those fractions is a number over x plus 5. And because that one is power 1, there's only one factor, one term that's in that factor. Now x minus 2 degree 3, so it's power 3. So we have to have 3 fractions matching that denominator. So x minus 2 degree 1, x minus 2 degree 2, x minus 2 degree 3. Because it was decomposing from that kind of denominator. But whenever the denominator is a power of degree 1, the numerator has to have lower degree. Degree 1, the lower degree than degree 1 is degree 0. Degree 0 as a function will be a constant number. So it's a number over this, a number over this, number over this, number over this. Those are all 4 factors that is a linear term. A linear term, we need degree 1. All right, over here we have 2 that is degree 2 term. For this degree 2 term, there's only power 1. So we only need one term in that denominator. Now, if that's the denominator, the numerator has to be degree 1 because the denominator is degree 2. So what is degree 1 function? Degree 1 function is mx plus b, a number times the variable plus another number. We're using a, b, c, d, e, f to indicate that we got to use different number. We don't know what those number is, but we know there got to be a number there. Also, this second degree 2 term has power 2, so we need 1, 2 to decompose the terms. that has those denominator, right? And then again, the numerator gotta be degree one functions, the denominator is power of degree two. Any question? So this is it, this is not the answer, but it's the beginning of the answer when you are trying to decompose this into. So whenever you have that thing, you want to rewrite it into several smaller fractions based on the formatting, based on the factors of denominator. We know after it's decomposed, it will look like this. But there's a little problem here. This question is so as how many numbers we have to solve? A, B, C, D, E, F, G, H, I, J. There's 10. So we got 10 unknown number we need to solve if we're decomposing it. So that was just illustrating the process of trying to determine the format before we actually solve this number. So let's look at an example that's not so lengthy. So this is the first example in the section about how do we simplify an integration function into a smaller fraction so we can actually work it out. So here's the process. So according to our idea, this question's denominator only have degree one factors. So we have factor x minus one that has degree one, factor x plus two that is degree two. So if this is decomposed into several small fractions summation, one of them has to be x minus one and the denominator plus numerator gotta be a number, and then two of them has to be x plus two. One is equal to one, one is equal to two. So whatever is the higher power, that power will be how many terms you need to match that. Maybe some of them could be a small number or a zero even, but you can't. You have to have all of them. So this is really the setting. We're set it up to know that if this is decomposed, those number has to be solved. You have to find them. This is basically decomposition process. Number one, you know how they were supposed to decompose to. You know how they look like, but then those numbers that was supposed to fit this equation, you have to actually solve them. Any question? Are we okay so far? So kind of understand the format. Let's talk about how to find those numbers. We're really going to go through an algebraic process. Whenever the question we need to solve has denominator, that always be a problem. So the way we handle denominator, we multiply both sides of the equation by the denominator. That'll cancel out the denominator. So in this case, the top line have equation that has a division. So denominator, biggest denominator is what we have on the left. So that denominator we multiply to both sides of the equation, which will get rid of the denominator on the left. So we cancel the denominator on the left. We multiply to the right side, and some of them will cancel, some will not. For example, the a over x minus one will cancel the x minus one, but you still have to multiply that. So you have a times x plus two squared. The second term we're distributing b over x plus two, cancel the x plus two. So you still have the b times x minus one times x plus two, and then the last one is c. The x plus two squared canceling c times x minus one. So after canceling common factor, you see how it looks like. Any question? Okay. To multiply both sides of the equation with the same term. Any questions? Okay, so after we cancel the denominator, this is how it looks like. So essentially, we're looking for A, B, C that is making the left side equal to the right side. And those A, B, C has to be true no matter what we say x value, because ultimately what's on the left side and what's on the right side are the same function. So with that in mind, we're gonna start. Okay, this equation is true. It should work for all x values. So what we can solve, we're trying to get what is A, what is B, what is C. Because decomposition, we need those A, B, C in order to solve the questions on the integration. So we're rewriting the whole thing, but ABC is unknown. We're gonna solve this coefficient. So this is I'm trying to write down the idea because this equation is supposed to work for all x values, like x equal 1, the whole thing equals x equal 2, x equal 3, x equal anything. So function is supposed to be true no matter what the x value. Therefore, what we're gonna do is this. We're making x equal to special value, so that the equation is easier to solve. This is representing those A, B, C are supposed to be numbers, but the x are variable. This is the equation that always is true for all x value. So number one, we see the x plus 2 in the equation. So we can make x equal to -2. -2 plus 2 equals 0. So if x equal to -2, x plus 2 equal to 0, that is 0, that is 0. So this is b times 0 essentially. That was a times 0. So the a and b will go away. So if we make x equal to -2, the equation is drastically shortened. So the left side is still 1. There's no a, there's no b because a and b are multiplying 0. And what we have is here x equal to -2. -2 minus 1 is -3. So we see that 1 equal to c times -3. So then we can solve for the c. c equal to -1/3. Any question? Are we okay?
So we just find numbers that cancel two of them out and then solve for each variable?
Right, because those number makes the equation easier to do. You can use other number, x equal to 5, x equal to 0, x equal to, but we're making x equal to a little special number because simply it's easier to take a shortcut. Any questions? Are we okay? All right, so we solved the C from that scenario. We really remember we're trying to solve the ABC. What is C, what is B, what is A. So now it's one step with one number we're able to solve the C. So we follow the same idea. Then we'll have to see the x minus 1. If x minus 1 equal to 0, x equal to 1. So if x equal to 1, x minus 1 equal to 0, so that's 0, that's 0. So the whole equation is again b times 0, c times 0, the a that's it's 1 plus 2. So that's 8 times 9, y equal to 8 plus 9. The equation again gets shortened, but this time the b and c goes away because b times 0, 8, c times 0, 8 times 9. So we have a equal to 1 over 9. We're able to solve the a, solve the c. We still need to solve the b. Right, so I think we run out of easy number because we got x minus 1, we got x plus 2. That's how I pick the number. I pick -2 and 1 just so it's easier to solve. Now we add a number. What do we do? What do we? I mean, we still have to solve for b, right? What do we do?
Plug in.
Plug in what number?
0.
0. Yes. Okay, so the easiest number that we can do is make x equal to 0. If x equal to 0, a lot of things will be easier. So for example, in the equation, a 0 plus 2 is 2. 2 squared 4. So 8 times 4. And a 0 minus 1 is -1. 0 plus 2 is 2, so that's -2. So we count -2. 0 minus 1 is -1, so c count -1. So if x equal to 0, equation become this. But then we need to remember we already know the number for c. We also already know the number for a. So a is 1 over 9, c is -1/3. So that means the whole equation, there's only one unknown. So that's why I leave it for the last one. I know the -2 and 1 is easier, which allows us to solve some number. We were supposed to solve ABC, take 3 unknown. And normally with 3 unknown, we need 3 equations. So we're trying to pick easier equation at first. Now there's no easy number, so we just pick possibly not number that's relatively easy to handle. So now we have to solve the B to do the algebra. Any question? So how do we solve that equation? Whenever the equation has fraction, what do we do? Solve equation that has fraction.
Multiply by the higher denominator.
Yes. So we're gonna multiply both sides of the equation with 9, and then we're gonna have 9 times 1 on the left side, and then 9 times 4 over 9 which is 4. 9 times -2, that's -18. 9 times 1/3 is 3. That will allow us to ultimately solve the whole equation. The 4 plus 3 is 7. 7 minus the 9 equals -2. So b equals -2/18, which is -1/9. Now we solve the A, the B, and the C. Any question? So then the method is okay. And then you see the steps. There may be multiple steps. Sometimes it involves a lot of algebra. So now we're able to find the A, the B, the C. And we bring that back to the original equation. We're done with the partial fraction decomposition. So the original function we want to integrate now becomes summation of 3 separate ones. So the original integration becomes integration of 3 separate ones. All 3 of them, the first 2, had denominator in 1. So those 2 you integrate using logarithm. That's 1/9 logarithm x minus 1. -1/9 logarithm x plus 2. So these 2 can be solved with logarithm. The antiderivative is logarithm. This one is different. This one is x plus 2 to the power of -2 with the power rule integration of x, a variable to the -2 power. Use power rule -2 plus 1 is -1. So this -1 power over -1. So after the integration, yes, -1 power. So x plus 2 to the -1 power, and also you cancel the negative sign. That's 1/3. This is also 1/3. The -1 goes away because we also got a -1 power of x plus 2. That's final answer to the whole question. You can see majority of the effort is on the partial fraction decomposition. The decomposition theory, the idea, it's very typical to follow those 2 rules, irreducible term or degree 1 term. But then the process, it depends on the question. When you have really long, big fraction, the decomposition can be a little bit tedious to work on. But if we're careful, we try to not make mistakes. I tend to make mistakes myself. Let's finish the first example. Do you have any questions? We feel like this is easier than the trigonometry stuff.
The harder.
So we deal with polynomial, but occasionally we might have to go back to trigonometry when the denominator gets big. So remember when the denominator is a term, we may have to complete the square in the denominator and the tangent substitution. So even with polynomial, we sometimes. Right, I'm not sure we got enough time, but we can start this. The second example, we're integrating this function. There's a little slight problem on this integration that is numerator degree 3, denominator degree 1 times degree 1, which makes it degree 2. So numerator is degree 3, denominator degree 2. Whenever you divide degree 2, degree 1, for example, you got x cubed divided by x times x. And it's actually x, right? But then you have other things. It's not a pure division, but we know there should be a degree 1 out of the division. And then this one, there's a little bit issue about this fraction. The numerator is degree 3, the denominator degree 2. This is an improper fraction. So we can't do the rule. Remember the rule when we're talking about the decomposition, we already mentioned numerator have to have smaller degree than the denominator. So when the numerator is higher degree, you can't not immediately do the decomposition to finish the division and then decompose the one that is proper. What's the improper fraction? For example, basically it's indicating the kind of fraction when the numerator is bigger. For example, you have 18 over 5. I mean, what does it equal? Finish your division, right? 18 divided by 5 is 2, right? 2 and then plus, there's 3, right? 3. There's 3, 5, and 18. And then we have a remainder that is, that was 3, yes, 3/5. So that is a proper fraction, 3/5 is a proper fraction, 18/5 is not. In order to finish the calculation for improper fraction, we first have to finish the division and have that one out, and then deal with that one. That was a proper fraction. So anyway, with that idea, we know this is what happened. We have to do division. I copied the textbook division here. So when you finish division, what do you have here? This is the divisor, x squared minus 2 minus 18 divided, this x equals to the quotient. And then over here, the remainder. The remainder will always have a lower degree than the divisor. So this turns it into a fraction like this. So after we finish the division, we can see this quotient, so we get x plus 2, and then the leftover is the one that still stay as a fraction. It's similar to what we are talking about. 18/5 is equal to 3 plus 3/5. So that one is a remainder. If this one was 0, this is actually divide out. But this did not divide out. That's not a factor. If this is a fraction, that would be 18. That would be 15. But anyway, we see similar things when we try to finish the long division. In this long division, numerator, denominator, quotient, remainder. Any question for this calculation is a long division that we did in college algebra. I don't know how familiar we are with the division process. Are we okay? I assume we were able to do this. Normally the process is you write down the numerator, write down the denominator, and think about division. X cubed divided x squared, you get x. And then you multiply x with this. You multiply that x with every term. That's how we get this one. This one is x times all that. It's like higher degree. And you're gonna do subtraction. Those two subtract out. But that one, if this 0 minus this give you this. 0 minus this give you this. So we switch the sign. And that one divide the x squared, 2x squared divided x squared. That's how we get a 2. And that 2, we're gonna multiply all the divisor. That's how we get this one. It's from 2 times 15 to 2x and 2 times x squared. Okay, that one. And then we're gonna do a division, subtraction, 15 minus 4. Subtraction, 15 minus -4. So that's how we get the 18. So it's basically a long division process whenever the numerature is 5 degree equation. Okay. So you can see after the long division, we now have this is easy to integrate. We now have a proper fraction. For that part, we are decomposing. Oh, we're about to run out of time. I guess we'll stop here. We'll finish the rest of the example in this section. Today is Thursday. I'll see you next Monday. Let me know if you have any questions when we're doing the homework. Okay, so feel free to send me a screenshot, send me the question, mention like which question or which section the issue on the side with the gentleman. Thank you.
Thank you.
Four hours per day.
This is all new to me. You also forget what
That mine. I feel like mine would have been a bigger.
It's okay. I think depending on where it is, usually
If you